Hi there, this is chapter 14 video lesson, and the main topic for chapter 14 is this concept of equilibrium. And reversible reactions is something that goes along with equilibrium. Up until now, we've only learned about completion reactions. So we have hydrogen and nitrogen forming NH3. We have this arrow pointing from left to right, from reactants to products. In the real world, though, a lot of reactions aren't just one-way streets like this. They're not just one direction. At the same time that this is happening, the reverse is actually also happening. The NH3 is turning back into H2 and N2. And that's what we call a reversible reaction. And we use this kind of fancy double arrow. It's actually kind of two half arrows. So there's one half arrow, there's the other half arrow, to show that it's reversible. When we see that reversible arrow, that two-way arrow, that implies that it's at a state of equilibrium, and it's kind of like a state of balance. We'll talk about the definition of equilibrium right now, actually. Chemical equilibrium is when the speed of the forward reaction equals the speed of the reverse reaction. So for every time that we turn chemical A and chemical B into chemical C, well, the exact same thing is happening in reverse. C is turning it back into A and B. So at equilibrium, every time we make a C, a different C is getting turned back into A and B. So again, the rate of the forward reaction is equal to the rate of the reverse reaction. And this is a dynamic equilibrium. One analogy I'll use later on is this concept of a seesaw or a teeter-totter. If you're familiar with what a teeter-totter is from like the playground from a little kid, one person sits on one side, there's a big board there, and you go back up and down, back and forth kind of thing. That, if we get to a balancing point on a teeter-totter, is what we call a static equilibrium. So think of on a teeter-totter, if you reach at a balance point where you're not moving, there is no motion. Now, a dynamic equilibrium is constantly moving. So it's not a static, chemical equilibrium is not a static thing, it's a dynamic thing. But since the forward and the reverse reactions are happening at the exact same rate, at the exact same speed, and at the same time, they kind of cancel each other out. So it's kind of a different kind of balance. It's a balance with constant motion versus a balance like a teeter-totter being stuck in a balanced spot and not moving. I'll let you read a lot of these notes. Le Chatelier's principle is a main concept of this unit, and it says that if we have a system, a reaction at equilibrium, and it's happy and it's balanced, if we do something to mess up that balance, if we knock it off balance somehow, and we'll talk about how we can knock these things off balance in a second, what it'll do is it'll try and get back to a new balance point. So again, Le Chatelier's principle says if we have a reaction that's at equilibrium, it's at this kind of balance point, and that is shown with that double arrow. If we knock that balance off somehow, it'll get back to a new balance point. So it'll try to get back to a balance spot. And there are three things that we can use to kind of knock a equilibrium off balance and make it shift back to a new balance point. So there's three factors. One is temperature. You'll want to remember these kind of rules here. if we add heat, the equilibrium will shift to use up that heat. So if you think about it, we have a reaction that is perfectly happy, it's balanced, you know, A plus B makes C and some heat. Just to review, that would be an exothermic reaction because the heat's a product. Now, if we have this reaction occurring in a container, and then we heat that container up somehow, it's like adding heat, it's raising the temperature, the equilibrium will shift to use up the heat. Now, this is actually a double arrow, if this is at equilibrium. And if we think about the forward reaction takes A and B and makes C and heat. So it's going to make more heat. The reverse reaction, which is going back to the reactant side, uses up C and heat to make more A and B. So in this case, if I added heat to this reaction here, it would want to use up that extra heat that we just added. So what we would say is the equilibrium shifts to the left, or it shifts towards the reactants. Or we could say that it'll want to use up more of the products to make more of the reactants. Because the reverse reaction, again in this case, C and heat coming together to make A and B, that uses up the heat. Remove heat is going to be the opposite. Say we have the same reaction, A plus B makes, or is in equilibrium, sorry. That is a really bad double arrow. Makes C and heat. Again, we have that reaction happening in a container, and then we cool that container down, we remove the heat. Well, it was happy before, and then we took some of this heat away. So this heat right here, since we cooled it down, we're taking some of that heat away. Well, what it's going to want to do is going to want to replace the heat that we're taking away. So we would say it shifts to the right. Because the right arrow, the right pointing arrow, the forward reaction, takes A and B and turns it into C and more heat. So again, if I remove heat, if I cool this reaction down, it'll shift right to make more heat, because if I take something away, it wants to replace it. That also works for chemicals. So let's say, again, chemical A plus chemical B in equilibrium with C and heat. If I remove some of chemical A, if I somehow go into this container and I pull some chemical A out, well, it was happy before I did that. And now that I took this A away, it wants to make more of that chemical A. So what it'll do is the equilibrium will shift to the left. It will use up this C and this heat to make more A and B. Because we took A away, it wants to make more A to replace what I took away. And same thing as if I added a chemical. If I added a bunch of B into the container, well, all that extra B, it doesn't want that extra B. It was happy, it was at equilibrium before I messed with it, and then I went and messed with it by adding more chemical B. Well, it's going to want to use up that extra chemical B. And if I think about it, I got two arrows going here. I got the forward and the reverse. The forward reaction uses up these two things, A and B, and makes more C and heat. So if I add B, it's going to shift the equilibrium to the right. It's going to use up more A and B to make more C and heat to reach this new balance point. It was at balance, and then I had to go and mess it up. Pressure is a bit different. You don't have to worry about this whole, if you remove something, it wants to make more of it. If you add something, it wants to use it up thing. Basically, concentration and temperature follow the same rule. That if you add something, it wants to use it up. If you remove something, it wants to make more of what you removed. Pressure is different. And pressure only has to do with gases. The only thing we care about are gases. So if you see really bat that top arrow, there we go. C plus, I'm going to add another chemical here, plus heat. Heat could be on the other side. We could have a endothermic reaction. We have a gas here, we have a solid here, we have a liquid here, and we have a gas here. The only thing that we're worried about is the gases. And let's say I'm just going to throw some coefficients in here. If we have 2 moles of chemical A plus 1 mole of chemical B, we make 1 mole of chemical C and 3 moles of chemical D. I don't care about solids. I don't care about liquids. I don't care about the heat. The only thing I'm looking at are the gases. And what I do is I just remember one of these rules. I remember that if I increase pressure, it'll shift toward the side of less moles of gas. I just remember one of them and then remember the other one's opposite. So increase pressure, less moles of gas. So if I increase pressure on this reaction, if I had this reaction in a container and I increase the pressure on it, well, it's going to shift to the side with less moles of gas. Well, here I have 2 moles of gas. Here I have 3 moles of gas. So if I increase pressure, it would shift to the left. It would shift towards the reactants. Now, if I decrease pressure, it will do the opposite. If I decrease pressure, it'll shift to the right. This equilibrium will shift to the right, we say, because it'll start using some of A and B up to make more C and D. So again, increased pressure, less moles of gas. Now, if we had a case where it was 2 moles of gas on this side and 2 moles of gas on the other side, basically pressure has no change, no effect. There would be no change. So that's the whole shifting of equilibria concept, and there'll be a bunch of questions in the practice quiz on that. I'm going to have one more video here, and that's going to talk about equilibrium constant expressions. So that's it for this video. If you have any questions on any of this stuff, send me an email or stop in on an off day.